Good evening, all of you. And we are going to start now our fourth seminar uh, conducted by the now Global Institute Kurunagala. And today we have selected the very first part of electromagnetism and electromagnetic induction lesson. And when we consider about electromagnetism, by the word itself, it gives the idea of the relationship between electricity and magnetism. Because we know that electricity is the most versatile form of energy, electrical energy, because it can be converted to other forms of energy very easily. Right? Now, therefore, today we are going to now study about how the electrical energy is converted to magnetism and the relevant effects we get as the first part of this unit. Then first of all, we discuss about a very common thing we can see in junkyards in Japan. Because you can understand very clearly, now in Japan, uh, iron ores are not available. Now therefore, they have to depend on iron imported from other countries, but from this iron, high quality steel is manufactured in the country. Now, therefore, really now they have a shortage of now iron. Therefore, even after using various types of metallic objects, uh, they collect all these scrap iron. We call this scrap iron. Normally, you can say now yakada sumbung, and then after that, what do we do? Now they are collected in several places known as junkyards. We call these places as junkyards. When handling, now loading and unloading of metallic pieces now found in junkyards cannot be done manually. The reason you can clearly understand that there are sharp edges as well as very sharp points there. Therefore, in such situations, they use a very simple technique here now. It is an electromagnetic crane. You can understand how this is very similar to a now crane, but the specific feature is here we get an electromagnet. We get an electromagnet as a disk here now. The special thing is when the switch is turned, because here inside this we find a very powerful coil. When the switch is turned on and current is supplied, what happens? This metal disc, really now it is a soft iron disc. Here now we get a soft iron disc. Then what happens? It becomes a very powerful magnet, and a considerable amount of pieces of iron get attracted to that metal disc. Then when we want to unload it, only thing is the supply of current should be disconnected. Then the magnetism is lost and the pieces of iron may fall to the now relevant place there. Therefore, this is one situation where an electromagnet is used. So here also we get the same thing. Now this yellow color disc becomes a very powerful electromagnet. Pieces of iron now get attracted to that. By that, loading and unloading can be done very easily. Here also we get a similar one. You can see that even metal rims and other things like here we get now they are attracted to the powerful electromagnet. Here we get the electromagnet, and to that these pieces of iron now get attracted there. Now therefore, now this is a very good example for the use of an electromagnet. So you can understand that there's a slight difference between an electromagnet and a permanent magnet. Here we get a permanent magnet. Right. Now, when we consider about a permanent magnet, clearly we know that there is a polarity. We get a north pole and a south pole. Even in an electromagnet, we get a north pole and a south pole. Then we know that if you think of the now magnetism found around a magnet, the magnetism is found only in a certain region around the magnet. We call this one as the magnetic field. And therefore, we get the second feature here now, magnetic field. If the magnet is a powerful one, the magnetic field is greater. Now, if the now magnetic power is low, magnetic field is found in a small region around the magnet in a three-dimensional now manner. We find this magnetism there. Therefore, we know that in a magnet, the magnetic poles are there. Even in an electromagnet, we get the same feature. Similar to that, in an electromagnet as well as in a permanent magnet, we get a magnetic field. Then when we consider this magnetic field, you can understand that it is made up of some lines called magnetic field lines. Therefore, we know that here now these lines are called magnetic field lines. Really, the exact definition given for these magnetic field lines is the path taken by a small north pole kept near the north pole of the given magnet. Now imagine now this one is a powerful bar magnet. And if you keep a small north pole in the middle here now like this, if you keep a small north pole here now, then what will happen? North and north, the like poles repel each other. As a result, what will happen? This small north pole may travel in a direction like this. You can get it here now. Therefore, this one is a relevant magnetic field line in that instance. But if you keep a magnet now somewhere like this here now, the north pole here now, then what will happen? It may take a path like this. So this one is also a magnetic field line. And if you keep a magnet somewhere here like that, then what will happen? North and north repel. Therefore, this may take a path like this due to repulsion here now. When it comes to the middle, what will happen? It may be attracted by the south pole. Therefore, it may complete a journey like this. Therefore, just remember now we define these magnetic field lines as the path taken by a small north pole kept near the north pole of the given magnet. Right? Therefore, when we keep these this small north pole in different locations closer to the North Pole, it may travel in different pathways. They are shown as the magnetic field lines. You should know only one thing here now. The direction of magnetic field lines is always from north to the south, or from North Pole to the South Pole. You have to remember that. When we consider about any magnet, we know that more magnetism is concentrated in certain parts here. Now, if you take a bar magnet, more magnetism is concentrated at the two ends. We call these as magnetic poles. So, magnetic poles are the regions of a magnet where more magnetism gets concentrated. Right here we get more magnetism, where more magnetism gets concentrated. Right. Therefore, we discuss about now several features here. Now, if we take now any magnet, you can get the poles there, North Pole and the South Pole. Then we get a magnetic field where we get the magnetic effect. And magnetic field is made up of magnetic field lines. And then we studied that there are magnetic poles where more magnetism now gets concentrated. So when we consider about an electromagnet, we get only one difference when compared with a permanent magnet. By the word permanent magnet, you get the idea that the magnetism lasts for a longer period of time. But in an electromagnet, the magnetism lasts or exists until there is a supply of current. Right? As soon as the supply of current is disconnected, the magnetism of an electromagnet gets lost. This is the difference you have to consider relevant to the magnets. Then if you want to observe these magnetic field lines, we can do a very simple experiment. You might have done this in previous classes. You can take a bar magnet like this. You can take a bar magnet, and on the bar magnet, you can place a piece of cardboard. On the bar magnet, you can place a piece of cardboard there. So you will understand that here now, after now placing in a piece of cardboard, now then after that what can we do? You can spread some iron filings there. We say after that you can spread some iron filings. Then what can we do? You can tap the piece of cardboard gently. Then what will happen? Iron filings may arrange according to a certain pattern on the piece of cardboard, now representing the magnetic field lines. Now therefore, whenever we want to observe the presence of magnetic field lines, we use iron filings in such situations. Now we discuss about the differences as well as the similarities of permanent magnets and electromagnets. Then when we consider the usage of permanent magnets, you can think there are various instances in our day-to-day life where we use permanent magnets. For example, you can think of in speakers. In speakers, you can see a permanent ring magnet there at the back of the speaker, and even in pencil boxes like that. And even then you can think of in certain magnetic doors, that means you can think of for opening and closing, right? We can use a magnet. Now when closing, what will happen? The door pane may get attracted to the magnet, and by that we can close the door firmly. Like there are various situations where we use permanent magnets. Now speakers, pencil boxes, and even you can think of now about chess pieces, and even you can think of in magnetic boards, or normally we call them as Maggie boards. Even in Maggie boards, we know that there are some buttons which are used to fix on the board. Now they are also having permanent magnets. Then the other type is called the electromagnets. We studied that in electromagnets, magnetism develops or exists if there is a current supply. Otherwise, there won't be any magnetism in such devices. Electromagnets are used in various places. Now, one is you can think of some electric motors. In certain electric motors, we get electromagnets. Then remember that if you take a toy motor, in that you find two permanent magnets. Therefore, remember that even in electric motors, most of the time we get permanent magnets, but even there can be electromagnets also in some of the electric motors. And you can think of another one now, electromagnetic crane, we discussed. Another one is the traditional ding dong bell. In traditional ding dong bell, also doorbell, we find an electromagnet. With the help of that, we supply and disconnect the current, and in each situation, what will happen? There's a bell cup and a hammer. Then the hammer now strikes on the bell cup, making a sound. Therefore, even in traditional doorbells, we find electromagnets. Other than that, here you can think of now this is an electromagnet. So when we consider about an electromagnet, you have to understand that there should be a coil. When making this coil, you can't use normal copper wires. The reason is when each and every turn touches with the other one, there may be a short circuit rather than passing current along all the turns there. Therefore, we have to use coil wires here now. Coil wires, or sometimes we call them as now insulated copper wires, or even we can use the word winding wires. We can call them as winding wires because we have to wind it around a soft iron core. Remember that when we supply current, the soft iron core becomes the magnet. They are not the coil. The magnetism is found in the soft iron core. Therefore, when making an electromagnet, a large number of turns of insulated copper wire is wound around a soft iron core. Then you should know that in order to have a very strong electromagnet, you can make several modifications in this. One is by increasing the number of turns of the coil. For the coil, sometimes we use a word called solenoid also. So, by increasing the number of turns, we can increase the strength of the electromagnet. The second one is now the cross-sectional area of the soft iron core. Right? If you use a small soft iron rod in the middle, the magnetism created is less. But if you can have now soft iron core with a greater cross-sectional area, then we can increase the strength of the electromagnet. The third one is by increasing the magnitude of current, I. By increasing the now amount of current we supply to this electromagnet, we can increase the now strength of the electromagnet. Then you must be able to remember that there are three ways of increasing the strength of an electromagnet. Number one, by increasing the number of turns of the coil. Second one is by increasing the cross-sectional area of the soft iron core. Third one is by increasing the magnitude of current. That means you can do that by increasing the number of cells. Like that, you can follow a strategy for this one. By increasing the magnitude of current, the strength of the electromagnet can be increased. So when we consider about the now metals attracted by magnets, mainly you have to consider about this one here now, iron. Then you get nickel, as well as you can go for cobalt. These are the three main metals which are attracted to a magnet. We have to discuss iron, nickel, and cobalt. Now look at this one. By now you must be able to now identify this accessory used in the domestic electric circuits here for home electric circuits. Now this accessory is known as RCCB. You should know this. Residual current circuit breaker. Earlier, this one was called as trip switch, but nowadays we have modified the term. In Sinhala also we say Sheshadara Paripatha Bindine. Right? Residual current circuit breaker. Then inside this we find two electromagnets there. Whenever there is now residual current, a current leak that goes to the earth through an appliance or through a person, through a consumer, then what will happen? The switch may turn off automatically. And you have studied that there's a test button here now. Frequently, at least once a week, you have to test this button. And when you push this button, what should happen? The switch should turn off, otherwise the RCCB is not working. That means there's a risk. So we have to replace it with the new one. Then other thing you have to remember that relevant to now this RCCB, we have to connect two wires there. One is the live wire should be connected, and even the neutral wire also should be connected for the RCCB. And here we get the other ones here now, like we call this one as MCB. In the distribution box in the home electric circuit, you find these pieces here now. MCBs, or normally we call them as miniature circuit breakers. But we call them as miniature circuit breakers, right? Singiti Paripada Vedina. And you can understand that here now, if you observe well, you can see the value here now, C32. The meaning of this one is, through this miniature circuit breaker, a maximum current of 32 amperes can be passed. If the current exceeds 32 amperes, imagine now the current is coming of the magnitude 35 amperes. Then what happens here now? This miniature circuit breaker MCB turns off automatically, now protecting the remaining part of the circuit there. Therefore, we know that in a home electric circuit, now we supply current to various parts through a miniature circuit breaker, to the living room, to the bedrooms, right, like to the kitchen, like we have to supply current through a stipulated miniature circuit breaker. Now, therefore, remember that in both, in the RCCB, residual current circuit breaker, as well as now in miniature circuit breakers, electromagnetism is used. That means inside these breakers, we find an electromagnet. Just remember that. So, we discussed and we defined enough terms here now. Magnetic field is the region or area, you can say, around the magnet where the magnetic effect can be experienced. We can experience the magnetic effect in that region. And we studied that magnetic field lines. The definition is really not required. Really, we define this as the path taken by the small north pole kept near the north pole of the given magnet. Then magnetic poles are the regions of a magnet where magnetism has got concentrated. Then we are going to now move another part, an important one. If you think of any current carrying conductor, we just say any wire where current is passing, right? Any current carrying conductor has a magnetic field around it. ඕනෑම විදුලි අරයි යන සන්නායකයක් වටේට චුම්බක ක්ෂේත්‍රයක් ඇති වෙනවා. Right? Here this phenomenon was discovered by a scientist called Austin. Right? This phenomenon now was discovered by a scientist called Austin. Right? The phenomenon is in a current carrying conductor, a magnetic field is created around that. To identify the now direction of the magnetic field, we use a method called right hand grip rule. We call this one as the right hand grip rule. Then you can understand a gripping means something holding firm. Right? Here we have to consider about power grip. If your grip power grip where we use thumb in one side and the other four fingers, right, are arranged together in the other direction to hold something firm. So, if you try to understand this concept, imagine here now the cylindrical one is the current carrying conductor. We get the current carrying conductor. Then the direction of current is given here now. So what should we do? Really, you can think of a pen like that as a current carrying conductor. If the tip of the pen shows the direction of the flow of current, you can hold the pen in that way, pointing the thumb in the direction of the current. You have to point the thumb in the direction of the current. Now, for that, you have to hold the now current carrying conductor, or now, if you just use a pen for that, you have to hold the now pen in the same way. Then you can understand that when the thumb is directed to the direction of current, the four fingers here now, the four fingers are arranged in a direction like that. Therefore, this is the direction of the magnetic field lines. Right? So, when describing the magnetic field lines, we have to go for only two things. One is clockwise, the other one is anti-clockwise. Right? We get clockwise and anti-clockwise. So, we can try this one by going for a simple explanation. When we go for this one here now, normally, in order to describe the now direction of current, we go for two conventions by considering the concept of an arrow. So, when we consider about an arrow, You just consider about an arrow like this. So, now imagine now there's a current carrying conductor like here now, and now imagine now this one is a current carrying conductor. Right now we get the right. Now we get the right, current carrying conductor. Right. The current carrying conductor is represented by an arrow. Now imagine now there is a current carrying conductor kept vertically. Vertically. That means from the now plane of the book upwards here now. If you think of your situation, right? If there's a current carrying conductor kept vertically, and if the current is flowing upwards, right? There is a current carrying conductor placed vertically, and if current is flowing upwards, then we have to compare it with the direction of the arrow there. So you can understand that if you observe it in this way, this one is a current carrying conductor, current is flowing upwards here now. Then if you observe from this side, now you have to think of about the concept of an arrow. Then the current carrying conductor is there. Now this is kept vertically, right? Then the current carrying conductor is there. Then as the direction is upwards, the arrow is coming upwards. When we observe from the top, we see the tip of the arrow. Now, therefore, we represent it like this. The meaning of this one is there's a current carrying conductor. The direction of current flow is upwards here now. And in this situation, if you use, right? Now if you use right hand grip rule, remember that it should be the right hand. Right hand grip rule. Now what should we do? The thumb should be pointed in the direction of current. That means the thumb should be pointed upwards when we consider about the plane of the paper. And when the thumb is pointed upwards, the other four fingers may arrange in a direction like this. You can understand clearly. When the thumb is pointed upwards, the other four fingers, right, here now, may point in this direction. Therefore, this one is the direction of the magnetic field. We describe this as an anti-clockwise magnetic field. Right? We describe this one as an anti-clockwise magnetic field. Then, if you think of the direction of current downwards here, now imagine now the direction of current is downwards. This situation here now. If the current is flowing downwards, in this situation you have to understand that now the arrow is going downwards there. We are observing from the top. Now we see the tail of the arrow here now. Therefore, we see the tail of the arrow. Therefore, we represent it by putting a cross there. Right? So, if you apply now a right hand grip rule for this one, then you have to arrange the now thumb downwards there, because we considered that this conductor is kept vertically. Therefore, the thumb must be pointed downwards. The other four fingers show the direction of the magnetic field. Therefore, you may get you may get a certain direction here now, the magnetic field. It is clockwise here now, right? Then you get clockwise magnetic field. Right? So, In a simple way, you can understand the concept now. Right. Then I have drawn now two conductors here now. Two conductors. Then imagine now I can put a dot here now. What the meaning of this? Now this one is a current carrying conductor. There the current is coming out of the plane of the paper or plane of the book. In my situation, the current is coming out of the board here now. Then if you arrange now right hand, indicating this right hand grip rule, you have to arrange your thumb. You have to arrange your thumb now vertically upwards there. Then the other four fingers show the direction of the magnetic field lines. Therefore, here we describe it as anti-clockwise magnetic field. Now we get anti-clockwise magnetic field. But in other situation, where I have put a cross, the meaning is current is going into the plane of the paper uh, or the screen. Now, if you are arrange now right hand in that way, the thumb must be pointed downwards to show the now direction of current. By the other four fingers, you get the direction of the magnetic field. Then you can describe it as clockwise magnetic field. Clockwise magnetic field. So, just remember that any current carrying conductor has a magnetic field around it. This phenomenon was discovered by a scientist called Austin. And to identify the direction of the magnetic field, we use right hand grip rule. This is the simplest and easiest one. In right hand grip rule, what do? We have to point the thumb in the direction of the current. By the other four fingers, we get the direction of the magnetic field. Then again, you have to join now within